Okay, we're going to talk about oscillations. Oscillations and velocity. And we're going to find a formula so we can calculate the velocity at any point of the trajectory of this oscillating system. So we have here our little spring, and this is your little mass. Okay. And then it's gonna, hold on, let me do here the picture a little more good looking. And we're gonna displace this object, this mass over here. So what do we have here is the displacement. Okay, that's your displacement. Let's call it A. And this is going to be the equilibrium point, x sub naught. And this one over here, well, let's make it a little more over here. So it's going to go all the way here. And this is going to be x final. And that's your amplitude. So your amplitude is going to be x final minus x initial. That's going to be the amplitude. And once you take it to the point xf, you're going to hold it there. So the velocity is going to be equal to 0. So the velocity is going to be equal to 0. So that's before you let it go, and then it starts to oscillate. So the total energy of this system, the total energy is going to be 1/2 of the mass velocity to the square, that's kinetic energy, plus 1/2 of kx to the square, where k is going to be the spring constant. So we got our k, which is the spring constant. So that's the spring constant. And that's because there's a restoring force coming this way. So the force is going to be minus the spring constant times the displacement. And you got your restoring force right here, which is going to be the responsible for this mass to be oscillating. This is a mass here, right here. So it's going to be oscillating. So let's calculate the total energy. So the total energy is going to be, equal to 1/2 of the mass, 0 to the square, plus 1/2 of k, and then x is going to be equal to a. So it's going to be a to the square. So this term is going to cancel out. So the total energy is going to be equal to 1/2 of the spring constant times the amplitude to the square. And you have here your total energy of the system. And we can use this equation again, this one for the total energy. And now we have that the total energy is equal to 1/2 of the mass velocity to the square plus 1/2 of k, which is the spring constant, times x to the square. But we know what the total energy is. The total energy is 1/2 of ka to the square. So it's going to be here, it's going to be 1/2 of k a to the square is going to be equal to 1/2 of the mass velocity to the square plus 1/2 of k x to the square, where this x is the position at any point. So we can get rid of the 1/2. So we have k a to the square minus k x to the square is equal to m velocity to the square. And then we can divide by the mass, everybody. We divide by the mass. So you cancel your mass here, and then you can factorize k over m. and then you got a to the square minus x to the square right here, and you get the square root of all this, and that's going to give you the velocity at any time. I mean, the velocity at any position x. For any x, you can get the velocity. For example, let's say that you want the velocity of this particle. You want the velocity at right here. And this point is going to be a divided by 2, which is at the middle of the amplitude. And when the particle passes through this point, the one on green, when it passes through this point, you want to find out what is the velocity. So we go to this equation over here. So we have k over m, and then we have a to the square minus, and it's going to be a over 2 to the square, because that's where you want to find out what the x is going to be equal to a over 2. That's where you want to find out what the velocity is going to be at the point a divided by 2. And then you got to get the square root of this, and that's going to give you your velocity. So your velocity is going to be at your velocity at a over 2 is going to be k over m, and then you got a to the square minus a to the square over 4. And you got to get the square root of all this. So that's going to be equal to, you can divide this k over m square root times the square root of, you can put here, this could be 4 divided by 4, which is 4 divided by 4 minus 1 divided by 4 is going to give you 3 over 4 a to the square. And then you can pull out the a to the square as an a. So you have a over here, and then you have the square root of k over m. And then that's going to be times 1 over 2, the square root of 3. So that's going to give you the velocity at a divided by 2. It's going to be that. Another thing is that the angular frequency is going to be k divided by m square root. So this is going to be equal to, a omega, which is the angular frequency, divided by 2 and a square root of 3. And right here you have the velocity of your particle at the point a divided by 2, which is at the middle of the amplitude. And there you go. You got another problem right there. And you have a formula, which is this one, which can come very handy to find the velocity of the particle in your oscillator and your harmonic oscillator at any position. Okay, thank you.